In this lesson, we're going to look at a very interesting problem and one that I have classified here as a mechanical explosion. So, what do we mean by a mechanical explosion? Well, we have two people standing together, initially at rest. So, little person M1, bigger person M2, standing at rest. They're going to push apart. So they're going to exert a force on each other. So there's going to be a force on 2 by 1 and a force on 1 by 2. And I hope we remember our action-reaction pairs. They have to be equal in magnitude, opposite in direction. And that's the explosion. Boom! They push off of each other, and then they're going to fly apart. So here they have them waving bye-bye. So the M1 particle is bigger, it'll move a little bit more slowly to the right, and M2 is bigger, move more slowly to the right. M1 is smaller, will move a little more quickly to the left, as we're going to see. And since it is an explosion, there are only internal forces that are giving energy to this system, to these particles. So there are no external forces that we are considering during the explosion process. We then have, if F equals 0, ma, right? Mass times the acceleration of the center of mass equals 0, so velocity is constant. The velocity of center of mass remains constant. The Newton's second law of momentum form, delta P over delta T equals 0, so momentum initial equals momentum final. Now, you don't have to go through that type of analysis every time you solve an explosion problem, but you need to know that for any explosion problem, you are immediately going to write down P initial equals P final and see where it gets you. So let's see where it gets us. So we have the initial momentum of the system is 0 because they're both at rest. They push apart, and we are told that person M1 is observed to be moving at a speed of 6 meters per second to the left. So that's why we have the M1 person moving to the left at 6. We know the mass of particle 2, so we can very quickly solve for the speed of particle 2, and yes, it is going to be less than the speed of particle 1 because particle 2 is more massive, twice as massive, and actually has half the speed. Well, to look at the total kinetic energy that was released, we know there was no initial kinetic energy, and then boom, we had our mechanical explosion, and our final kinetic energy is based on 1/2 mv squared of each of the particles. So we had 54 joules of kinetic energy into the system coming from the force push. So that was the energy that was released. Well, how much of that energy went into M1 and how much of that energy went into M2? Well, if we take the 1/2 mv squared from only M1, that's our 36 joules. 36 divided by 54 is 0.666666 or 0.667. So 2/3 of the total kinetic energy actually went into the lighter particle. And that means then 1/3 of the total energy went into the heavier particle, because the heavier particle in this case was twice as heavy. But keep in mind that had the M2 been heavier and heavier and heavier, more massive, more massive, more massive, it would have moved less and less and less, and more of the kinetic energy would have been transferred to M1. And that's kind of what I want you to take away from this page of notes, is that the lighter the mass M1 is, and the more massive M2 is, the more kinetic energy is going to get transferred to M1. And we'll talk more about that actually in Chapter 10, our next chapter. Well, as far as the forces are concerned, we know F equals ma. And to calculate the force that they exert on each other, I am simply going to use the constant acceleration equations. And you could focus on particle 1 if you wanted to, but I chose to focus on mass 2. So we know V2 final equals V2 initial plus acceleration 2 times time. We calculated that V2 final was 3 meters per second. So that's why we have the 3 meters per second here. They started from rest, so the initial velocity was 0. Acceleration of particle 2 is what we're looking to solve for, because we want to plug that in for A2. And we were told that the time that they pushed apart for 0.5 seconds. So for half a second, they pushed apart. And that means the acceleration of particle 2 was 6. We plug in 6 for the acceleration of particle 2 times the mass, and we get 24 newtons. And of course, we have our action-reaction pair, so the force on 1 by 2 would have to also be 24 newtons. And if you wish, you can certainly do the same calculation focusing on particle 1 to confirm that you will get 24 newtons for that as well. So, interesting problem. We don't always think of pushing apart as an explosion, but for physics and problem solving, you definitely want to think of it as an explosion. And again, let me erase my ink here, so you can copy down all of the annotations if you want to pause it here and copy down all of your annotations. And if you have any questions, of course, we will discuss it together.